Hello and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. We previously released an episode where we talked to an expert in low temperature PEM fuel cells. And in that episode, we talked about and referred to other fuel cell technologies. Since then, we've had loads and loads of questions about alternate fuel cell systems. So in order to answer some of those questions, we've lined up a real expert in the area. We've got Mark Selby, who's the Chief Technology Officer from Ceres Power, and he's kindly agreed to come on the show and talk to us about what they do. So thank you, Mark, and welcome to the show.
Thanks, Ryan. Thanks for having me.
And if we could just get started, Mark, with a bit of an introduction to yourself. I know that the story of how you came to be doing what you're doing is interesting from what I've seen of it. So if you could just tell us about your personal background and how you came to be doing what you're doing now at Ceres.
Yeah, sure. I guess if you start right at the beginning, I'm a classic engineering geek. I guess as a kid, I had some really great role models as engineers, even if maybe I didn't call them that at the time. I mean, I grew up in a family business, so everyone around me was very hands-on. My dad could fix anything. His uncle I didn't meet, but he was chief electrical engineer in the local mines. So there were always stories that had around engineers that had some sort of halo around them, and that always really excited me. And I guess I got into computers and programming and electronics really early as a teenager and quite enjoyed it. Was quite good at it. So engineering was natural.
Right.
I went to Leeds and did electronics and computer engineering as a degree, and I was slightly obsessed with F1 at that stage, so I ended up doing a PhD in control and vehicle dynamics.
Oh, wow.
And I had this great supervisor called Professor Dave Croller, who I guess some people in your network might know, who was a real character, legend, extremely Dave, direct, proper legend. Taught me quite a few new words over the course of supervising me.
Yeah.
But it was a really sort of formative period. I think I got the bug for being quite direct and challenging assumptions about the right way to do stuff, and I think I really picked that up off him.
Yeah.
I ended up working at a few consultancies like Pi Technology, and ultimately ended up at Ricardo.
Right. And
that was really the last thing I did before I moved into this sort of clean tech space. And I guess there were a few things. I spent a few years as a consultant, and I loved it. I learned a lot. It was really interesting. It was really varied. But I guess it's a bit like fast food. You go and have a burger and some fries, and you feel full immediately, but then you immediately feel starving very, very quickly and slightly unsatisfied. And I saw this slightly wacky at that stage startup in Ceres that was just up the road. And I had a friend there, and I got talking, and it felt like it was going to be a 7-course meal. You were going to be really satisfied, and you were going to try a lot of different things in the journey. So I think that was really what sort of drew me to where I am now, actually. And they were doing something different, so it sort of fitted with quite a lot of my personal ethos around challenging what's normal and what can be the next step.
Right.
I think automotive at that stage felt very incremental, even though I was doing stuff that was really state of the art and cutting edge emissions work. It still felt very incremental on what was in a production car at that stage. So doing something a bit different felt really exciting at the time.
And so were you, when you were consulting, were you mainly working on kind of conventional combustion engine vehicles and that kind of thing?
Yeah, I mean, I was doing I did a few different things, but I guess on the emissions side, I was working mainly on either very highly downsized gasoline engines, and looking at control strategies to make them more drivable. But also I did quite a lot of work on sort of next generation diesel emissions. So 3 or 4 years ahead of production, looking at different strategies and the control strategies and OBD strategies that you needed to make them all work. So I think I guess in production, it was Euro 3, Euro 4 when I was working on that sort of stuff, and we were working on strategies for sort of Euro 6 and beyond.
Yeah.
So quite a few years ahead of production.
Oh, wow. So really big leap then to go from kind of engine-based work to fuel cell technology. That was quite a transition.
Yeah, although it felt quite natural. I mean, I guess in some ways it was no bigger leap than going from vehicle dynamics to engine emissions,
right?
Which was already the step I'd been on. And I think that came because I've got a background in controls. And I think one of the things that you learn as a controls engineer is to pick up domains very quickly and try and understand the physics so you can try and understand how to control them.
Yeah.
So it's something on the journey, I think, around controls and systems engineering that enables those leaps to feel relatively small steps in some ways. There was always some transferable analytical skill that you could bring to any domain.
Yeah. Oh, wow. Okay. So you moved across to Ceres to start your 7-course dinner. That was quite a few years ago, wasn't it now?
Yeah, I mean, it was in 2006. I was still a pretty young software engineer at that stage, controls engineer. I joined Ceres and started really from a blank sheet of paper in a lot of ways, which is really nice to be able to say, well, what were all the things I saw done really, really well in the automotive industry, and what can I bring over, and what things did I not like, and what things were legacy that we can cut away and leave behind. So
yeah.
It felt like we were able to make some really big productive steps and do some things in some really best-in-class ways. And I think that's one of the nice things in those early stages of companies. You get to make your own choices. You're not necessarily hanging on someone else's legacy in the next journey.
And that must have been pretty early days for Ceres as a business, so quite a small team at that point as well. Yeah,
I mean, I think there were about 45, maybe 50 people there when I joined.
Okay.
I think Ceres sort of founded in 2001.
Right.
Although the research had been going on since probably the mid-90s, and the sort of real sort of genesis story goes back a lot further. But the research started in the mid-90s, and then Ceres founded in 2001, I think, and that was really on that wave of late 90s, early 2000s hydrogen buzz.
Yeah.
Ballard, all of those sorts of big stories.
Yeah.
Real classic hype cycle stuff in a lot of ways.
Yeah.
But I think one of the things I found when I joined Ceres, yes, it was a small team. Yes, it was quite young. It lacked a lot of process. Everyone was quite young, but they were super bright and they were super driven, and everyone cared about doing stuff in the right way. So people were prepared to sort of put down their sacred cows and learn really fast. And that was really exciting journey, actually.
Yeah.
Bumpy journey in that sort of first few years I was there. But it was you learn a lot.
Yeah. And could you just give us a bit more about that the Ceres kind of background and where it came from, just to kind of fill that gap in? Because I guess I've heard of Ceres. A lot of people might not have. So just if you could fill in where Ceres came from.
Yeah, okay. I mean, I end up telling this story a lot. It's a story I love, actually. So the guy that founded Ceres was this guy called Professor Brian Steele, and I never met him. He died in the early 2000s before I joined Ceres. But when he was a young academic, he went on a trip to North America, and he ended up going around an Allied Signals laboratory, which is everyone now knows as Honeywell. And he saw one of the first, and we'll talk about fuel cells in a bit, but he saw one of the first solid oxide fuel cells, which is the temperature domain we work in. Solid oxide in those early days was all ceramic. It was extremely high temperature, nearly 1,000 degrees. And it's got some really interesting properties. It's very efficient. It can consume any fuel. It produces electricity in an incredibly effective way.
Yeah.
But it had all sorts of problems. And he saw that right away in the 60s. His take was they were fragile. They wouldn't last. They'd need to be made out of really rare materials. Engineering a system around them would have been really hard because you're into super nickel alloys and sort of aerospace grade materials that can cope with all of those temperatures.
Especially in the 60s.
And he said and he said that'll never work. It'll never ever be commercial, even though it's got all these really interesting properties. And he went away and he thought about it for about 30 years. I mean, literally sort of mulling on this problem. And he worked out that you had to lower the temperature. You had to find some way of getting away from these all ceramic systems and start thinking about hybrids with other materials to get the mechanical properties. And you really need to think maybe that efficiency wasn't the absolute be all and end all. It was about creating a whole system that created value for someone who owned it. And I often think, as an academic, probably in the 60s, that was a pretty prescient way to think about a technology. And I think even today, I don't think every academic I meet thinks in that really commercially grounded way in terms of the research problems they're going to go after.
They tend to get a little bit obsessed with over-optimizing, in their particular domain without thinking at that high level. So very
and it's unfair. And I think it's unfair to say academics should do what entrepreneurs and technologists in industry should do. But I think recognizing that problem and not falling into that trap of the sort of the better mousetrap thinking, I think was a really interesting idea. So in the early 90s, he started some research council program with some money from EPSRC. I think he got maybe £300,000, and he started doing research on how you would combine mixed conducting ceramics. It's a bit technical, but you need a ceramic that can conduct oxygen ions to make a high temperature fuel cell. And he thought about how you might combine some of those materials with steel. And the traditional materials that people were using, you couldn't turn them into ceramics at less than maybe 1400, 1500 degrees C. Yeah. So you couldn't combine those ceramics with steel without destroying the steel.
Yeah.
So his real breakthrough in the 90s was to find a ceramic that had the right properties to be a fuel cell, that also sintered at a low enough temperature not to damage the steel, and to find a steel that was low cost in its own right. And he brought all of those things together at the end of the 90s. And that was, he went to business school at Imperial, and at that stage they ran this early startup competition in the business school, combined an MBA student, an academic, and tried to matchmake them with some what we'd now call angel investors. I don't think that phrase existed then. But that's really how Ceres started. And I guess the background to the name Ceres is that material that he found is a material called ceria. And that's a metal named after the Greek goddess of the harvest, which is Ceres, which is why Ceres is called Ceres Power, because we're grounded in how we use and exploit that particular element on the periodic table.
Oh, wow. Fantastic. And that, because I was going to ask about the steel cell technology, but you've kind of answered it there. So there's a whole lot more meaning to the name steel cell than just steel, the material.
Yeah, there is. I mean, it's completely coincidence in a lot of ways. But yeah, we spell it with the extra E? So Brian's name had 3 E's in it. So in practice we don't, because you can't patent that sort. You can't trademark that sort of stuff. But yeah, the steel cell has real resonance, especially for a few of the colleagues in Ceres who knew Brian.
Right.
I mean, I think one of the very sadly he had cancer in the early 2000s and eventually passed away in about, I think it was 2004.
Right.
But the company hadn't actually made any power out of one of these fuel cells, and he lived long enough to see the company actually make a complete fuel cell work.
Oh, wow.
And his wife said that was the thing that kept him going. We've kept sort of a relationship with the Steele family over the years. They're still investors. It's really nice to see them and hear some of the stories about Brian in his pomp.
Right. Wow. So can you tell us a bit more about the steel cell and how it does actually work?
Yeah. Okay. I mean, so I guess I've got this vision that one day everyone will know what a fuel cell is. A bit like we know what a battery is, and a bit like we know what an engine or a motor is. I mean, you don't necessarily need to know what a Carnot cycle is to know what an engine is. But what's a fuel cell? So fuel cell, and again, I use this phrase quite a lot, is the most efficient way of converting chemical energy into electricity known to physics.
Yeah.
Now, that's a really powerful thing. If you can start any story with, it's the world's most, you're onto something that's intrinsically interesting and potentially commercially valuable.
Yeah.
So fuel cells are a bit like batteries. I mean, they're in the same class of class of science. It's all what we call electrochemistry.
Yeah.
And a bit like batteries, I think everyone knows that there are lots of different chemistries for batteries.
Yeah.
They might not have thought about it, but they know a standard supermarket battery is an alkaline battery, and they know they've got a lithium-ion battery in their phone. They know that there's a lead-acid battery in their car.
Yeah.
And fuel cells are similar. In that field of electrochemistry, there's a lot of fuel cells. And fuel cells, you talked earlier about your previous podcast of proton exchange membrane fuel cells.
Yeah.
There's solid oxide fuel cells. There are alkaline fuel cells. There are molten carbonate fuel cells. So there's all sorts of classes, different fuel cells. But I think the two most important at the moment are the PEM fuel cells that we talked about.
Yeah.
And solid oxide fuel cells.
Yeah.
And I think it's always dangerous to talk about winners. I tend to think that this is an ecosystem, and there's going to be quite a few of those chemistries that are going to find commercial applications that are only relevant to one particular chemistry.
Yeah.
So what's great about those proton exchange membranes? They start instantly. They're extremely high power density. They're very flexible. You can turn them up and down, but they're not actually that efficient compared to say some other technologies.
Right.
And they need ultra pure fuels, and maybe it's quite hard to hit some of the cost targets and hit very long lives that you might want for an energy conversion technology.
Right.
I think one of the things people tend to forget is car only runs for about 10,000 hours in its life.
Yes. Yeah.
Whereas if you've got a power station, it might run for 80,000 hours in its life.
Yeah.
So it's really the engineering challenges and technology challenges are quite different between those two domains.
Yeah.
I mean, I can run a PEM fuel cell in a lab for as long as it needs to live in the field forever.
Yeah.
I can do that over and over again, and it doesn't really affect my development cycle. Whereas in the other sort of technologies, maybe need to last longer because they're really there as primary energy conversion technology. They need to be much more efficient. They need to hit those cost targets, and they need to predictably last for 10 years.
Yeah.
Maybe 15 years. So that's solid oxide fuel cells. The advantage of solid oxide fuel cells is rather than requiring pure hydrogen, they can run on anything from pure hydrogen to dirty hydrogen through to natural gas to ammonia to LNG and LPG. Even things like diesel can be put through these high temperature fuel cells with the right fuel processing.
Oh, wow.
So solid oxide fuel cells are really, they're sort of omnivorous. They eat anything.
I like that.
And they're extremely, extremely efficient. They're sort of maybe 10 to 20 percentage points more efficient than a PEM fuel cell.
And where does the name come from? It's quite an unusual name. I think it's interesting in terms of where that comes from.
What, PEM and solid oxide?
So the solid oxide element, yeah.
Yeah. So what happens in a PEM fuel cell is hydrogen comes up to this membrane and sheds some electrons, and the proton that's left in the middle of a hydrogen atom goes through the membrane.
Yeah.
So that's why they're called proton exchange membranes.
Yeah.
What happens in a solid oxide fuel cell is that you have this solid membrane, and some oxygen comes up to the membrane, gains some electrons and becomes an oxide ion, and then goes through the solid oxide membrane.
Yeah.
So most fuel cells are named after the charge carrier.
Yeah.
Again, a bit technical. So you've got proton exchange, you've got solid oxide, an oxygen atom with 2 electrons. You've got alkaline fuel cells, which the charge carrier is an OH ion. Yeah. You've got molten carbonate fuel cells, in which you have a molten salt through which the charge carrier is a CO3 anion. So you end up naming fuel cells based on the charge carrier is really where it comes from.
In my ignorance, I'd kind of assumed it was something to do with the materials it was made out of rather than that characteristic. And I think I don't know, it might just be me being daft on that, but I think a lot of people think the same.
There's some overlap if you think about it.
Yeah.
the charge carrier in a molten carbonate fuel cell, you have to have a carbonate salt in order to make it a charge carrier.
Yeah.
In a solid oxide membrane, it turns out it's a metal oxide.
Yeah.
So I suspect you could get into a debate about what's right, but I think most of them are really named after the charge carrier.
Right. Okay. What sort of applications then? So you've sort of touched on a couple. We're saying like super high efficiency. You said was an advantage. Omnivorous. It can eat anything. I love that. I'm definitely going to use that again. So I'm going to steal that one. Is a positive aspect. But you mentioned the sort of maybe not quite as power dense as a PEM fuel cell. So what kind of applications then does that mean solid oxide fuel cells are kind of finding a home in? I guess there's a different applications, different needs and requirements that suits the different sorts of fuel cells.
Yeah, applications is a good one. I think applications for fuel cells, the safe space for solid oxide fuel cells has always been stationary power. Power density doesn't matter. Cost is king. Efficiency is king. Don't really care about weight. And that was really, when I started, that was really how we thought about solid oxide fuel cells. On the journey we've been on, one of the things we always believed was that steel combined with ceramic must be intrinsically more robust than a ceramic on its own. And we started in maybe 2012, 2013, when we started to hit all of the cost and performance targets, to look at what attributes we really needed to push if we wanted to make the technology more applicable. And this really comes back to our business model, which we haven't talked on, but the key thing for Ceres as a licensing business was to try and make the technology go into as many markets as possible. So once we were good enough in that stationary application, we said, okay, well, what do we need to add in order to, or confirm in order to make it applicable to more things?
Yeah.
So we started to really test things like robustness, and it turned out we were amazingly robust. And actually, again, if you can say that world's most thing, I think we really are the world's most robust solid oxide fuel cell by a country mile. It's a sheet of steel. You can bang it. You can throw it around.
Yeah.
Importantly, you can warm it up incredibly quickly. If you imagine taking a hot glass and you put it into water or vice versa, you'd expect that ceramic to shatter.
Yeah.
Whereas what we can do is take a cold sheet of steel with this very thin ceramic coating on it and hit it with 650 degree air and see the whole thing warm up in a few minutes.
So it's the inherent kind of brittleness of the ceramics and expansion contraction conditions that is a limiting factor.
Exactly, and that turns out that manifests in a few other ways. So can you load cycle an all ceramic fuel cell very quickly? Well, actually, if you do that enough times, you'll see ceramic failures.
Yeah.
You'll see brittle failures. But with a steel cell, because it's got this intrinsically tough substrate, again, you can load cycle it very fast. You can warm it up, cool it down very fast. Turns out, and no one would have thought this a few years ago, you can also stick it on a vehicle and drive around with it.
Okay.
So one of our big applications at the moment, and I don't think from a business point of view it will be the biggest of all of our applications, but it's a super important market, is range extenders for commercial vehicles.
Okay.
So at the moment we're doing quite a lot of work in that space with one of our partners, Weichai, which is it's interesting. In the UK, almost no one's ever heard of Weichai. But if you look closely, it turns out they're the title sponsor of Ferrari Formula One team.
Yeah.
And they are the world's largest maker of diesel engines.
Yeah, huge Chinese company.
Yeah, absolutely enormous. And they came to us and said, could we help them engineer this technology onto a bus?
Right.
And their concern is there is a drive to clean up Chinese cities. There is a lot of pressure for electrification in China. It's part of their multi-year plans.
Yeah.
They looked at pure electrification, and that works. And they've got electric buses in their portfolio. But they also look at, well, if I put a fleet of 50 buses in, what do I need to do to the grid infrastructure to charge all those buses?
Yeah.
And what's my fleet utilization?
Yeah.
And what's my range? So then you start looking at fuel cells for buses, and I guess you can approach that in two different ways. You can say, well, I'll have a really big fuel cell and small battery, and I'll run my bus and use my fuel cell almost as if it was an engine.
Yeah.
Or I'll have an electric bus with a very small fuel cell, and I'll let the batteries manage all the dynamics of driving, and I'll let the fuel cell keep trickle charging the battery system. And that's what you call a range extender rather than a fuel cell bus.
Yeah. It's interesting that's because in the early days of fuel cell buses, the vehicles that were coming out tended to have really huge fuel cells that, big old Ballard sort of 150 kilowatt units, and they were just a nightmare to keep going because they didn't like being cycled, and I mean even the PEM ones didn't really like being cycled. The market's progressed to this sort of hybrid fuel cell system.
Yeah, and I wouldn't say any of those people to take that approach were wrong. I just think the world's changed. I think if you look back to, the real champions of this, and I think the whole industry owes companies like Toyota and Honda at the end of the 90s a massive debt of gratitude for pioneering the idea of doing this. But I think if you looked at some of their hypotheses when they started those programs, there was an assumption that fuel cells were this mature technology and would rapidly come down a cost curve, and batteries would never come down a cost curve.
Yeah.
And therefore you say, okay, well, if that's going to be the case, I'm going to end up with big fuel cell and small energy store.
Yeah.
And what's happened for all sorts of reasons, probably really starting with smartphones and the R&D that went into lithium ions as smartphones really got deployed, transformed energy stores in automotive and meant that now batteries in cars have hugely come down a cost curve. Yeah. So now you end up with very low cost energy storage, and the fuel cells maybe haven't made the progress either in R&D or in volume that was predicted back in the 90s by Toyota and Honda.
Yeah.
So actually, when you take a sort of system engineering view of that, you end up in quite a different place in terms of your cost optimal product that meets the consumer's requirements. So I think you're going to see a lot more shift towards much more hybridized concepts, if you like. I mean, they're all hybrids, but big battery, small prime mover rather than big prime mover, small battery.
Yeah, and particularly those applications, city buses are horrendously transient in operation. So you can have easily a bus with a 300 kilowatt powertrain that the average power consumption is like 20 kilowatts. It's up and down and stop and start, and same delivery trucks. A bit less so for kind of long haul trucking, but it's still, I think it's a lot more transient than people realize. So kind of balancing out your power production and keeping the fuel cell at its sweet spot versus then managing all of that variation in the drivetrain. And then, of course, recovery of energy as well, because you can't, well, I'm going to say this and you might contradict me, but the thing that you can do with a battery is recharge it, under braking, and you can capture energy that way. But with a fuel cell, you can't do that particularly easily. Yeah,
I think in this application you wouldn't do that.
Yeah,
I think it doesn't make sense to try and do that in this application.
Yeah.
I think the other thing for us with those applications is, if you're going to put all of your money on the horse that says there's going to be a hydrogen infrastructure everywhere, you're not really going to be able to sell that application, that product across the region. So I think one of the things you'll see companies like Weichai and others making multiple bets, and they're already doing this. So they will have hydrogen-only technologies that will be operated in places like Shanghai and Beijing, but they'll need to think about what happens to decarbonising and cleaning up the whole of the country where there isn't necessarily a hydrogen infrastructure.
Yeah.
So you start off with a natural gas or omnivorous fuel cell range extender, and where you've got hydrogen, maybe you use it. Yeah. The economics are still really challenging, actually, on PEM fuel cell buses, or maybe you have a natural gas fuel cell bus. So I think you're going to see a real ecosystem of products that reflect the variation in infrastructure around big countries like China, or even around the UK and Germany. I can definitely see in the UK, the M1, London, Leeds, Newcastle, having a hydrogen infrastructure. Whether that in the next 10 years is in every small town in the country where there's a petrol station, I'm not so sure. So I think you've got to think about what's the whole journey to that end state energy transition.
Yeah.
And I think one of the big things around solid oxide fuel cells is there a real no regrets choice? Now, that's to some extent true in automotive, but it's also more true in power generation. If you deploy a technology today, you need it to be super efficient and make the best use of the resources that we have access to. So if you deploy a fuel cell today, maybe you can save a third to a half of the carbon in the local application where you've deployed it.
Yeah.
If there's a carbon-free energy vector in 10 years in that same place, well, the same technology still works. And you've done all of that work to pull it down the cost curve and drive the volumes up by making that no regrets decision.
Yeah. What is it about a solid oxide fuel cell that allows it to be omnivorous?
It's temperature. I mean, if you think about it, hydrogen is relatively easy to work with, and the energies around how that you turn hydrogen into an ion need really good quality catalysts like platinum. In a solid oxide fuel cell, you can use the temperature to enable that to happen more easily. So we still use catalysts. Ceres is a catalyst in its own right. In fact, no one's ever heard of Ceres, but it's everywhere. If you've got a self-cleaning oven, it's the catalyst that's coated on the walls of your oven to decompose fat.
Right.
It's in a three-way oxycat in a normal gasoline diesel engine.
Right.
It's if you've got any white glass in your house, it's typically the dye they use to put into glass to make it white.
Oh, wow.
It's such a commodity material, they turn it into nanopowders to use as polishing agent on touchscreen TVs and mobile phones. It's part of the material that you use in a flint lighter to make the spark. So it's one of those materials, again, that no one's heard of, but it's about as abundant as copper.
Yeah.
And it's used industrially and in products all over the place.
Oh, wow.
So, but using it at temperature means that things like natural gas decompose very easily into hydrogen in their own right. But also the materials are compatible with the CO and the CO2 and the hydrogen that comes off that sort of decomposition step.
Right. And is that, because we sort of had these debates in the past about some people talking to us about burning hydrogen in combustion engines, and we sort of don't like that because you still have a combustion process there, so you get combustion byproducts, even regardless of the fact you've got quite a clean fuel. Is it similar sort of mechanism in a solid oxide fuel cell? Do you have kind of, it's not combustion, but decomposition byproducts coming out?
No, because we don't. I mean, the things that tend to drive those byproducts in a combustion engine are pressure and the amount of oxygen and the temperature you're operating.
Right.
So, as with any chemical reaction, you sort of need, the pressure, the temperature, and what my mix is, and what you'll get out of it.
Yeah.
If you think about burning hydrogen in a combustion engine, or even in an external combustion flame like a gas boiler,
yeah,
you'll get some NOx. In a fuel cell, we operate very lean and at very low temperatures, so you don't get any of those products. You still produce CO2 if you're running on natural gas. We clearly don't produce CO2 if we're running on hydrogen, but we don't get any NOx or SOx or particulates or any of those products.
Right. And I guess the CO2 production from a natural gas would be less than, if you were burning a diesel or another fuel like that.
Yeah, it'd be much more efficient than diesel. I mean, what's the typical diesel engine efficiency? 20-25%, maybe pushing 30. You get to big truck engines a little bit higher, whereas in a fuel cell today we're at 65%. And I think by the end of the decade you'll see products in excess of 70, maybe approaching 75% at those sort of larger scales. So even the world's very best combined cycle gas turbines today are only in the mid to low 60s.
Yeah.
And because of the way we run them in the energy system, they're somewhat further south of that again.
Yeah.
and then you have to ship it from that central power station to a home to where it's consumed.
Yeah.
So even with the very best central generation technologies, you might be lucky to get 50% efficiency out of that molecule of natural gas to energy in your kettle. Probably more like 45, whereas we can stick a 65% power generation device in a small office and sit it in the corner of the room and you wouldn't know it's there, and it's 10-15% more efficient than that.
And you don't have to worry about an exhaust scrubber to get rid of all the NOx particulates.
You don't need to worry about any of that sort of stuff. And also, because you're doing it where you need it, maybe you can reclaim the heat as well and get up to 98% efficiency.
Yeah,
so when you think about it in terms of total energy system perspective, it's really powerful.
Well, that's been one of there's a huge potential for combined heat and power, and there was a massive sort of surge in combined heat and power, but then the huge problem with combined heat and power in cities is you're then transferring, basically gensets running on gas into the city centre, which you've got local then emissions to deal with from that. So huge potential.
If you do it with engines, you do it with engines. I personally think engine-based CHP doesn't really make sense.
Yeah.
I know there is a business case in certain applications. I think the business case is being eroded by the cost of low carbon electricity. But I think the carbon case has gone. 10 years ago, probably even less, but certainly 10 years ago, there was a really strong carbon case for even genset CHP.
Yeah.
When you look at the decarbonisation of the electricity grid, there's no case for doing it unless you're, I would say, significantly north of 50% efficient electricity.
Wow. Yeah. I know you said omnivorous before, but something just popped into my head there. So could a fuel cell deal with something like a so-called like dirty fuels, like a methane, wet methanes and things like that you get off anaerobic digestion or kind of?
Yeah, and interestingly, there's it's a bit of a niche application, but there is some real benefits to doing it. And this is really quite tech, I guess. But it turns out if you take methane that's got a load of CO2 in it, you can recover the waste heat in the fuel cell and convert that CO2 back to a fuel that the fuel cell will self-consume. And that's a process called dry reforming. Ooh. So actually using biogas is a really efficient thing to do in a fuel cell. Now, it's not a big enough market at this stage for us to put a lot of effort into going after. Right. But there are some really interesting things like that maybe don't pop out unless you really think about the thermodynamics.
Well, it's funny because, biogas as a thing in Europe it's not a massive thing really, and anaerobic digestion stuff is not. It's certainly there's a lot of potential for that to be much bigger technology in Europe, but in certain parts of Asia, South Korea has invested massively in anaerobic digestion. They process all their food waste, through that kind of system, and they're much more into that than we have been. So there's lots of, that you can't get a huge amount of useful energy from domestic waste because it is sort of so wet and full of junk, unless you digest it down. But we don't really do that yet. So I can see the potential in that. So, market application point of view, you've got the obvious one of stationary power that we touched on. And I guess that's going to be like huge kind of megawatt scale fuel cells, right down to localized CHP stationary power type applications. So that's a pretty big market in itself, like global kind of energy production. You've got, you mentioned range extenders for commercial vehicles like buses and trucks, I guess, as well. Are there any other kind of applications that you see coming through on top of that, or is that your kind of main?
Well, there's some pretty big buckets, aren't they? Sort of stationary stuff that's still and stuff that moves.
A couple of $1 trillion industries right there.
So I guess I think the thing I find that's really interesting is when you find applications that have really powerful business cases that maybe people haven't unpicked. And we talked about range extenders and why that's maybe a business case that people haven't looked at before. And it's about fleet utilization, and it's about grid reinforcement, and it's about all those good things that maybe don't get factored in when people just think about the pure cost of an electric vehicle.
Yeah.
In stationary, the one I think is most exciting and will be really transformative over the next couple of years is data centers. So most people think about stationary power and they say, well, I consume electricity and it's a bit variable. And if there's a power cut, it's a nuisance, but there's no problem.
Yeah.
Whereas if you're an Amazon or a Google or an eBay, if you have a power cut in your data center, that is billions of dollars in minutes lost in terms of e-commerce.
Yeah.
So the value of reliability in your power is enormous. So if you look at a data center now, and these things are pretty big, people talk about building data centers. When they say how big is the data center, they talk about megawatts.
Yeah.
They talk about, they literally name their data centers in terms of the power consumption.
Yeah.
So they say it's a 10 megawatt or a 15 megawatt or whatever it is. So you're starting to talk about some big numbers.
Yeah.
But then you look at it and they build them out. And so every rack's got a UPS in, and then there's a building scale UPS. And then you walk outside of the building and then there's a row of diesel gensets for when the power cut's too long to run through the UPSs. And then they're worried that diesel generator might not start. So they have a second row of diesel gensets. And then they're worried that one might not start. And to get to this 5 nines reliability, they typically have 2 layers of UPSs and 3 rows of gensets for the whole power consumption of the data center.
Yeah. Wow.
Just to get those sort of 5 nines reliability, because the typical grid is maybe 2 nines, so 99.9%.
Yeah.
So if you look at the value of reliable power and what they're prepared to pay for that 5 nines reliability, actually a massively redundant array of fuel cells, maybe 1,000 10 kilowatt fuel cells, is a much better way of doing that because it's got a lower carbon intensity.
Yeah.
There's only a single step, and you get your reliability from that diversity of products.
Yeah.
And you've got big enough volumes that you can pull it down the cost curve very quickly. So if in a normal office building, maybe you can justify $1,500 a kilowatt for a 10 kilowatt, 65% efficient power station, in a data center, you might be able to justify $3,500. Because when they built that data center, they were allocating 25% of their capex just to the cost of reliable power. So there's a really powerful business case there in terms of what you do. So for me, the deployment of fuel cells over the next few years, whether it's in stationary or motive, will be about really those business cases that create way more value than the incumbent solutions. And that's where the disruption will happen first. And then you'll start to see them spreading out as the volume happens into more and more markets.
Right. And if you can, I mean, you mentioned Weichai earlier, but if you can you talk about some of the things that you're working on now, what you guys have got kind of in the back room?
Yeah, for sure. I mean, I think the fuel cell technology is really world leading now, and you start to see people like Bosch and Weichai invest in many, many tens of millions of pounds, both in Ceres, but also in their own programs to exploit Ceres technology.
Yeah. So
you'll see a lot more companies come alongside us and build relationships with us in that way.
Yeah.
An example of a program we signed maybe 9 months ago now was with a Doosan Corporation, which is another extremely large company in Korea.
Yeah.
So I guess one of the big things that's different about Ceres is we're prepared to collaborate in a really active way with progressive companies like Weichai and Bosch and Doosan to get to the market at pace and at scale. So in some ways, it'd be really nice to say that's done.
Yeah.
And fuel cells are here. They're completely nailed on. I think they are, but the R&D in that area never stops. But what we're also seeing is a huge increase in the wider hydrogen economy. So green hydrogen, where does that come from? Technologies like electrolysis are really important.
Yeah.
So one of the big things we're working on now, which is one of the things I'm most excited about, is the work we're doing on electrolysis. So you said, could you charge a fuel cell.
Yeah.
And really, that's what an electrolyzer is.
Yeah.
Now, I don't think you'd end up with a bus that was running in electrolysis mode when it was going down a hill. That won't make sense.
Yeah.
But high temperature electrolysis definitely does make sense. And the reason it makes sense is because it's close to 100% efficient, whereas PEM electrolyzers may be only 60% efficient, or an alkaline electrolyzer is maybe 70% efficient. So because of the fact you can recuperate this high quality heat, because the temperature they operate at, you can get almost the same energetic hydrogen out as you put renewable electricity in. So high temperature electrolysis is a big area of research for us. We started talking about it for the first time as part of an investment round in January where Bosch increased their stake in Ceres. So that's one of the things that occupies most of my mind at the moment is how we really accelerate that.
There's some pretty big. There's been big in Europe. Programs been announced which are like using renewable energy to generate clean hydrogen, but then almost sort of talking about completely decoupling sort of wind farms from the main grid and just literally having the wind farm there to run electrolyzers, and then taking the hydrogen as the primary product rather than using it as a, because people have often talked about using it to like peak shave on renewables, but there's been a few of those, and they're like huge multi-megawatt scale projects that are being kicked around at the moment in Europe. So would you see your kind of technology fitting into those areas as well?
Yeah, definitely, and probably more so than some of the other technologies.
Right.
I think if you, I mean, there's some great documents around this. You might have come across something called the Energy Transitions Commission, which have written quite a few really interesting white papers on this. And when you look at this sort of decarbonisation journey over the next 10 to 30 years, let's say that sort of timescale, almost every hard to decarbonise application that you look at, whether that's steel or cement or aviation fuels, green hydrogen has got a role to play in all of those. Yeah. And green ammonia has got a role to play potentially in shipping as a fuel. Yeah. But it also is required for feeding about a third of the world's people. Yeah. So green chemicals, and I starting to talk about the age of electrochemistry being a really important thing. Yeah. Fuel cells and electrolyzers are a bridge between molecules and electrons. There's nothing else that can do that in science. So when you start to roll forward and you think about the end of the combustion era, and you look at the next 20 years, green chemicals, green hydrogen are going to be enormous. When you start to try and put numbers around that, it's somewhere between 2 and 3 times the size of the current oil and gas industry. Wow. Talking about multi-trillion dollar industry by 2040. Wow. In order to go on this decarbonisation journey. So you're dead right. At the moment, and for the last decade, people have thought about electrolyzers as a way of managing intermittency. Yeah. And they're probably going to think about that for the next decade as we increase renewables. Yeah. But once we've got enough renewables just for power, we're going to have to go further than that. We're going to have renewables that enable green chemicals. I mean, I guess put it in context in the UK, the electricity grid is something like 50 or 60 gigawatts. The gas grid is something like 400 gigawatts. So if you start to think about our consumption of chemicals energetically, that means you're going to need 5 or 6 wind turbines for every one that's running the lights in your home. So we're not going to stop deploying renewable energy. Once we've got enough for our electricity grid, we're going to start deploying it towards these green chemicals. So that area is massive, and it's bigger than oil and gas. Big opportunity there in Europe, and particularly the UK, where often for sort of current chemical production or materials production, it's the energy cost is cited as being like a main disadvantage to siting operations in the UK and in Europe. But with new technology like that, if you can create a level playing field, that starts to get really interesting in terms of that. Yeah, I mean, I guess the cost of energy is an interesting one, isn't it? I mean, there's a few ways of comparing things, and I think we're usually overly simplistic. I mean, wind in Northern Europe is probably the lowest cost wind in the world, maybe with the exception of Patagonia and Chile. But when you actually look at it, it's a very low cost place to produce wind when you look at the infrastructure and where we consume it and the ability to get the energy you produce in a turbine, someone who's actually going to use it. You look at the Middle East and solar is very low cost. When you look at hydrogen from electrolysis, in almost every scenario for every technology, it's totally dominated by the energy cost. So it's right to look at it in those terms. But what we don't do with oil and gas is look at all the external costs. So I sat on a panel a few years ago with a US engine guy, and he said, well, fuel cells will never compete with how much I can make an engine for. And he's right, but that conference happened to be in Florida. And it was very easy to sit there and say, well, look, we're in a hotel and the beach is already right up to the bar. Give it 10 years and we'll be 10 feet underwater. So are we going to start putting the loss of Florida on the BOM cost of your engines? America's had 2 wars in the Middle East in the last 20 years that have cost billions and billions. Do we want to put that on the BOM cost of engines around the world? Because primarily those wars are about maintaining communication lines with sources of oil and gas. So when you start to look at the external costs, and that's before you even get into the air quality issues, and you look at the lost GDP. And there was a paper a couple of years ago that said, if you look at the service industry, the worst air quality days in London are worth about 8% on productivity. You look at a city like London, you look at the GDP contribution from the service industry, and you say, well, would cleaner air be worth it if it gave me 6% back on my GDP? You probably would, wouldn't you? So we don't necessarily think about all of the costs that are assigned to our current way of living. And I think when you compare that with those greener alternatives, I don't think people will make quite the same flippant, it's too expensive comments.
And I agree completely. I think particularly with the current situation, public health is there's lots of links being made with sort of public health and air quality and to sort of how well people are doing through the current situation. I did see one really interesting paper, and it was talking about using. So obviously, one of the other big challenges we've got as a planet is the availability of fresh water, and it's a huge problem. Desalination is something that people do, but it's very expensive. Massive carbon footprint from current desalination technology, and really interesting that. People looking at using fuel cell technology to essentially decarbonize desalination and make that work better. Is that something that you've seen much of?
It's not something I've looked at the economics of. I mean, I'm aware of it. I'd be interested to know whether the economics really do stack up. I think if you look at most of the places where there's water stress. The Middle East and those sorts of areas, it's not obvious to me that burning more of a chemical vector is necessarily the right way to do it, when maybe building a concentrated solar thermal plant might actually be a more rational way of doing it. I don't know, and I think that's really, I don't think that's necessarily a technology choice question. I think that's really a sort of macro energy system question about how that'll pan out. So it's not something I've really thought through in terms of any economic detail.
Just to start to wrap up, what are you kind of really excited about in terms of what's coming in the future for Ceres and in the industry in general?
I think I'm really excited about the opportunity that Ceres got. I mean, I think when you look at the journey we've gone on. I mean, think about Ceres. We talked about that hype cycle in the 2000s, and that was really a technology push phase. Now people are pulling really hard on this technology. So it's here, whether that's Cummins in the US or Weichai in China or Doosan in Korea or Bosch in everywhere. It's happening and it's real. So I'm really excited to have gone on a journey where everyone I talked to had never heard of a fuel cell, to where at least a few people I talked to know what a fuel cell is. And I think I'm really excited over the next few years to be able to see it become a really mainstream and important technology. And I'm really excited that Ceres has survived to be a real leader in that space. I think it's a massive testament to the talent of colleagues and the amazing group of people and mentors that I've been fortunate to work with. So I guess I continue to be really excited with the partnerships we build and the types of people we're getting to work with around the world. I find that both culturally and technically really interesting and stimulating. So for me personally and for Ceres, I think more of the same, more growth, more partners, new applications like electrolysis. I think I'm really optimistic at the moment that we can see how we achieve change quickly. And I think if there is a bright side to what's going on with the current COVID crisis, it's actually when people see something tangible in front of them, they act in a quite rational way to really address those.
Yeah. It does. Do you see, because, I mean, obviously in Asia, they seem to have made some huge investments in hydrogen, and then actually just even this week, there were more announcements in terms of additional hydrogen investments, and the Koreans have really gone for it. Japan have really gone for it.
I mean, there's a fuel cell in the Korean parliament.
Yeah.
I mean, there's a Hyundai fuel cell in the lobby of the Korean parliament. They're so excited about it. It's really central to what they do. You can't change the world from one country. I mean, I think one of the things that frustrates me, if we're slightly negative for a second, is we sometimes take a slightly parochial view. Okay, how does the UK decarbonise, and how do we achieve green growth in the UK?
Yeah.
Well, if there isn't green growth globally, there's not going to be green growth in the UK. So it's a global opportunity as much as a global problem.
Yeah.
And I think we need to think a little bit less parochially about how the UK plays in a global technology market. And at the moment, we're doing that really well. Ceres is a really good example of that. There's lots of others in around the UK. ITM in electrolysis is a great example of a company that's playing globally.
Yeah.
There are lots of others, and I think we should celebrate what we're really good at, and it's getting technology out of the lab and into the world in a really effective way.
Yeah, I completely agree. Brilliant. All right. Okay. So thanks so much for that, Mark. I've really an absolutely fascinating conversation. I've learned so much there, and my head's hurting a little bit, if I'm honest. So that's absolutely fantastic, and it's great to see your passion and your depth of knowledge on the subject. It just absolutely blown me away. So thank you so much for taking the time out to do that with me today.
Thanks, Ryan. Really enjoyed that.
Well, I hope you enjoyed that as much as I did. That was absolutely fascinating. Mark's passion and knowledge come across so strongly when he's talking about fuel cells and the technology and its applications and how important it is going to be. I think fuel cells kind of had a bit of a bad press because of this previous hype cycle. They're really coming strongly back into their own. We're seeing lots of activity in the market. Recently, big flotation in the US with Nikola, which is making fuel cell and battery electric trucks, and that's a big part of their story. Some huge investments coming out of Asia. Hyundai did a huge release this week as well on fuel cell technology. Daimler and Volvo merging activities together on fuel cells as well. Lots of stuff, lots of stuff going on. It's definitely a technology that's been around for a while, but as Mark very clearly made the point, fuel cell isn't just one thing. There's lots of different kinds of fuel cells, and there will be some winners and there will be some losers in amongst that. But I really do wish Ceres all the best. Fantastic to see a great British success story there in terms of their technology and how that is coming into the market. So great to see them doing some really good work and continuing to grow. So I hope you've enjoyed that. Don't forget, if you haven't already, please subscribe. You'll get notifications of the shows as and when they come up. Don't forget to check out our back catalogue. We've got lots and lots of other really interesting shows sitting there now. We're well into the 50s in terms of number of shows that we've done. I'm not going to say exactly because I'm not sure what sequence we're going to publish the last few in as we put them out. So, but well into the 50s now in terms of shows. So lots and lots of great information there on electrification technology, clean tech in our space. So also, if you have a question, this show very much came out as a result of feedback from listeners on one of our previous episodes. So if you've got any questions or anything you'd like us to pick up, please don't be shy. Send those in, and we'll look at those. We'll either answer them directly, or we will produce an episode just for you on your question. So that's all we've got time for today. Thank you very much for taking the time to listen to me. Again, I really look forward to speaking to you again soon.